So an application of this tangent line and the derivative that we've been doing connects to kinematics, average velocity, and looking at speed and time. So we've got a variable of velocity, we've got a distance that we're traveling, and we've got a time. So we've got a function that distance that you travel is related to the time it takes you to get there. Okay? The average rate of change with respect to time of an object moving along the line between 2 points is just the slope. So if we look at a picture here, and you had time here, and you had distance here, and you went from this point to this point, this secant line, its rise over its run, if, for example, you traveled 2 kilometers and it took you 10 minutes, then you would be, your average speed or velocity would be 2 over 10 kilometers per minute, if those were the units that you were using. So your change in distance over your change in time is just your average velocity. And that is very much connected to our secant lines and our tangent lines. If you wanted to find the instantaneous rate or instantaneous velocity, how fast were they traveling at this moment, we could use one of those tangent formulas. So we're going to do a question here, and we're also going to get really good at using some cool features of our graphing calculator. So the position function of an object is given by this formula, where s is the distance in meters and t is time in seconds. And we want to just find the average velocity of the object over the interval from 0 to 3. So we could figure out what it is at 3. It's at a distance of 104. And we could find its distance at 0 by plugging in 0. This one's much easier to calculate, and we would get 5. So if we wanted to find our average velocity, which is just your change in distance over your change in time. Your change in distance was 104 minus 5, and your change in time was just 3. And this works out to be 33 meters per second. Now I'm going to show you on the calculator. I'm going to open up the calculator here. Oops. I'll move it off to the side so you can copy things down. And I'm going to take this equation s of t and put it into my graph. Of course, you don't have the t button, so you're going to put in. All right. Looks like everybody's got stuff written down. So I'm going to show this here. I typed in the equation into y equals. Now a couple things. You could hit graph, and you could look at what this graph looks like. And if I wanted to, as in this question, right, I had to figure out what s of 3 was. So I'm going to show you a couple things that are really cool with the calculator. One you already know, right? One that you already know is you can calculate a lot of things from your graph by going second calculate. And one of the things you can do is a value. So I can push enter, and I can plug in 3 this way and get 104 for my graphing calculator that way. But something you might not have known with your calculator, and I'm going to go back to my regular screen here, is that if you have the newer calculator, you can hit alpha, and you have these menus across the top. And one of the ones, F4 menu, gets to your y variables. And if I choose y1, because if I go to y equals, that's where I type this graph in, you can actually use function notation in your graphing calculator. Check this out. What's y1 of 3? It should be 104. Sure enough, it works. Okay? For those of you that don't have the newest version, you can go to the vars button and then over to y variables and number 1 on functions. They're listed there as well. So I could get y1, be like, ooh, I want to find out what y1 of 0 is. And it's equal to 5. In fact, I could even do something like this. If this was, I could put my fraction, I could do y1 of 3 minus y1 of 0 over, I hope you wouldn't write 3 minus 0 in. You could hopefully do a little bit of mental math. But if that's tricky for you, write down 3 minus 0. And when I push enter here, I get the 33 all at once from my calculator. So that is a really neat option that we have on our calculator. We can use functions and function notation. You can also get that from your graph as well. Instantaneous velocity is the slope of a tangent at a certain point. So if you look at your average rate of change and you made your time go to 0, your secant line would get closer and closer to your tangent line. And your instantaneous velocity is the slope of your tangent line at that point. So this is the same formula that we had when we had when we had x goes to c of f of x minus f of c over x minus c. But we've just changed the variables here to be time. But it's exactly the same formula. So here we have a rock dropped from a bridge that is 240 feet above a river. The distance in feet from the river is given by the following function. Does anybody know what gravity is in feet per second squared? 9.8 is meters per second squared. Negative 9.8 is your regular gravity. Have you ever done American physics where you had to use feet per second squared? It's 32 point something, yes. Okay. It is no coincidence that this number here is half of 32. So find the velocity at 3 seconds. So what would we have to do? We would have to find the instantaneous velocity by doing the limit as your change in time goes to 0. And so what do? Time is getting close to 3. We have t minus 3 on the bottom and s of t minus s of 3 at the top. And again, I can go to my calculator here, and I'm going to go to y equals just for fun. And I'm going to clear this out, and I'm going to put in negative 16x squared. What was it? Plus 240. And I can do y1 of 3 to get 96 that way is sure a lot faster than plugging it in. So here's my original equation, s of t, negative 16t squared plus 240. S of 3 we just calculated to be 96. And it's our hope with a limit, right? Because right now you plug in 3, you're dividing by 0. I'm hopeful that the top factors so that I can solve this. Well, we do a little bit of math on top, subtract the 96, I get 144. I can factor out a common factor of 16, which would leave me with t squared minus 9, which is a difference of squares. And then nicely, our t minus 3's cancel out. So we plug it in and we get negative 96 meters per second. Your calculator also has instantaneous rates of change shortcuts built into it. So check this out. Okay, I'll wait for you guys to finish writing that down. Yes. Oh, right, it should be. Thank you for the units. We're just so used to using, it should be feet per second. Excellent. So what we just did is we found out that if you drop this, right, if you drop this stone, at 3 seconds, that's how fast it's going at that instant. It's increasing in speed because gravity's pulling it faster and faster and faster. This is not a good game to play with your friend, where your friend stands below the bridge and you drop stones and they try to catch them. Not a good game because it could be going faster and faster and faster. You're like, oh, let's catch a big one. No, not a good idea. Okay? Now, on a graphing calculator, I've already typed this equation into our calculator. And we figured out that y of 3 was 96. If you hit your math button, we are going to find that the instantaneous rate of change is your derivative. So if I go down to number 8 and do derivative, our variable is x. We could type in our equation here, but we've already got our equation in y1, so I can just do y1 as a shortcut. And I can find the instantaneous rate of change anywhere by just telling them what I want x to be. Which is really nice, because we can figure out 3. That's what we wanted to figure out, was the negative 96. If I put in 3, sure enough, I get 3. If I do this again, I could find out how fast is it going at 1. If you dropped a stone, what is your prediction? Would it be going faster or slower? I'm going to guess slower. Sure enough. You're at the bottom. Oh my goodness. Well, we'd have to figure out when it hits. When does it hit 240? We could solve for that. We could plug it in. Oh, now I want to be at the bottom. If you plug in 0, right? Distance 0 here. Move the 240. 240 divided by 16. And square root that answer. It's the square root of 15. So it takes the square root of 15, almost 4 seconds to hit the ground. You can even write square roots in here. You're at the bottom and you're trying to catch this. How fast is it going? 124 feet per second. That's going pretty fast already if you're catching that stone at the bottom with your friend. Oh, here. We skipped ahead. I was predicting the question. So we figured out that time would be square root of 15. Why don't I need the plus or minus here? Yeah, negative time doesn't really make sense. So I don't mind if you're in the habit of doing the plus or minus. You did that and then just say the only one that makes sense is the square root of 15. And then we'd have to do this. Isn't it nice that I had it in my calculator already? That I could just get the value from my calculator? But if we had to do this by hand, you would have to plug in this, which we already know this should be 0. Any suggestions with that square root? You could either, at this point, multiply by the conjugate, or you could factor the t squared minus 15 as a difference of squares, even though 15 isn't a perfect square. At this point, those would simplify and you could plug things in. If you wanted the exact answer, it's 32 root 15. And we got it from our calculator to be negative 123.935 anyways.